Hi everyone, this is Elena Lubintseva again, and in this lecture I will go over the key concepts of Chapter 5 on the atmospheric pressure and wind. In this lecture, I will talk about the nature of pressure and wind. We will discuss the major forces that determine wind speed and direction. I will discuss some local and regional examples of wind systems. And finally, I will talk about the general circulation of the atmosphere. Let's start by defining what is wind. Wind is simply air moving either horizontally or vertically over the surface of land. Wind develops as a result of spatial differences in atmospheric pressure or atmospheric gradients. As you know already from the previous chapters, atmospheric pressure is the weight of the atmosphere on a surface of land, and pressure is measured by a device called a barometer. As you know already from the previous chapter, warm air is always lighter, and so it's moving up. As it's moving up, it's then cooling down because the atmosphere is colder as we move upward with an altitude. And as it starts cooling down, it starts sinking down in a different location. And this is what creates the high pressure. So this cold air, which is moving downward, is the cause of the high pressure. So this creates a gradient, right? We have a warmer place with upward movement air, and we have the colder area with high pressure. This creates the gradient, and the air starts to move from the high pressure into the low pressure. And this is basically what the wind is. So wind always tends to be associated with those gradients of pressure that are in turn caused by the gradients of the temperature. And the wind would be then blowing from the high pressure zone into the low pressure zone. This speed typically would be the greatest during the daytime when we see also this greatest contrast between the temperature in extremes that are causing differences in the pressure. Here is a picture of the weather station, and I want to point at a couple of typical instruments that we use in order to record the direction and the speed of the wind. So the speed of the wind is typically measured by the device called anemometer, and we can measure the speed of the wind in various units, kilometers per hour or miles per hour or knots or meters per second. And the direction of the wind is measured by another instrument which is usually put on top of the anemometer, and this is called a wind vane that simply shows in what direction the wind is blowing or where it's blowing from. Wind direction is named according to its source rather than the destination. So the wind from the north blowing towards the south is called northerly wind. And most meteorological observations report wind directly using one of these 16 bearings, for example, northwestern wind or southwestern wind or northern wind or northeastern wind and so forth. So remember, we are always referring to the source of the wind rather than the destination or direction of the wind. So wind and pressure, of course, are very closely related because it's the gradient in the pressure that is causing the wind, and so the speed of the wind is closely linked to the intensity of this gradient of the pressure. On the weather maps, you will see pressure indicated by the isolines. Those are the lines of the same pressure or permanent pressure. They're called isobars. And you can see the lines every 4 millibars, for example, 996 millibars and 1000 millibars, 1004 millibars, and so on. And this typical range of pressure would be between 960 and 1050 millibars. When we look at the pressure map and you see those maps in the book, you can clearly see that when the isobars are very closely spaced, that means this is where we have very strong pressure gradient. And when we see this pressure gradient force being the greatest, this is where we would see the highest speed of the wind. On the other hand, in the areas where these isobars are very are spaced very widely, this is where the pressure gradient is low, and then the light speed would be also very light speed of the wind. So high-speed winds develop in the areas where the isobars are very close, and low-speed wind are in the areas where isobars are far away. This diagram illustrates the relationship between the pressure gradient and the speed of the wind. Take a look and tell me, what do you think? Where do you see the slowest wind and the fastest wind? And of course, the wind is always blowing from the high pressure to the low pressure. This relationship between the pressure gradient and the speed of the wind applies to any scale. The pressure gradient force is the primary force influencing the formation of wind, and this works from the local systems such as breezes to the global systems such as major cyclones, major tropical cyclones all over the world, and other atmospheric systems. So this force is determined by the spatial atmospheric pressure at any given moment of time. The gradient of the atmosphere, this is what determines the speed of the wind from the high pressure to the low pressure. As you can see in this example from our chapter, if you look at the difference of 120 millibars versus 1010 millibars on the left, and compare it to the difference of 1020 millibars to 980 millibars. The second gradient is 4 times larger, it's 4 times more intensive. So in this case, the wind speed will be also 4 times greater than in the case where we had 0.1 millibar per kilometer gradient. So the wind is blowing from the high pressure to the low pressure, but not along the straight line. In fact, we would see the straight line corresponding to the pressure gradient if it was not to the Coriolis effect. But the Coriolis effect is caused by the rotation of the Earth, and the Coriolis effect is deflecting everything which is moving in the northern hemisphere from its straight line to the right, and in the southern hemisphere it deflects everything to the left. To visualize it, you can imagine walking on the merry-go-round, and you would see how difficult it is actually to follow the straight line, because you would be deviated by the movement of the merry-go-round. Exactly the same is happening to wind, to water in rivers, to the ocean currents as a result of the Coriolis effect. The strength of the Coriolis effect and the way how it influences the wind at different latitudes depends on how far away we are from the equator. The magnitude of the Coriolis force varies with the velocity and with the latitude of the object. So the Coriolis force is absent at the equator, and its strength is increasing as we are moving to the North Pole and the South Pole in both hemispheres. An increase in wind speed also results in a stronger Coriolis effect. So the faster is the wind, the stronger is the Coriolis effect, the stronger is the deflection. However, we have to keep in mind the Coriolis effect does not have influence of it does not influence the speed of the wind. The speed of the wind is determined by the pressure gradient, but the intensity, the magnitude of the Coriolis effect is determined by where is the gradient. So the higher is the latitude, the higher is the Coriolis effect. So these two forces in the atmosphere, the pressure gradient force and the Coriolis effect force, are opposite, and they balance each other as they determine the direction of the wind. If we look at this graph, you will see the geostrophic wind. So the geostrophic wind is parallel to the isobars. So it's perpendicular to the pressure gradient. Both the geostrophic wind and the gradient wind are really sort of those idealized situations that are happening if we are assuming the absence of all other forces. But in the reality, there are some other forces associated with the friction of the surface of the land itself that are influencing movement of the air as well. So the surface winds on the weather maps don't blow exactly parallel to the isobars as in geostrophic wind or perpendicular to the gradient. Uh, Close to the Earth's surface, friction associated with different land use, land cover surfaces reduces the wind speed, and which in turn also reduces the Coriolis effect. So, for example, the wind can be affected by the surfaces such as cities or agricultural lands or the surface of the ocean or mountains. So this is the concept of friction. Friction is the resistance between the contact surface of two bodies in motion, and this friction can be much stronger if, let's say, we're talking about the same wind blowing over the mountains or blowing over forested area. That will slow the movement down compared to a smooth surface such as the ocean. We are going to look at the major atmospheric systems, major weather systems associated with pressure gradients, and those are cyclones and anticyclones. Cyclones are associated with low pressure, and anticyclones are associated with high pressure. And so in the northern hemisphere, because of the Coriolis effect, the air is moving in the cyclones in the counterclockwise direction, and it's moving in the clockwise directions in the anticyclones. In the southern hemisphere, the movement is the opposite. The air is moving in the low pressure systems in the cyclones in the clockwise direction, and it's moving in the counterclockwise direction in the anticyclones, which are high pressure systems. So as we could see earlier, the warm air is expanding, it's lighter, it's moving upward. The cold air is contracting, the molecules are moving closer to each other, and the air is denser, it's sinking down, and it creates the high pressure zone. The wind is blowing from the high pressure zone into the warmer, low pressure zone. The same is happening close to the Earth, but the same is also happening in the opposite direction at the higher levels of the atmosphere. So you can imagine that as the warm air is moving upward, it then cools down, it creates the high pressure at a certain altitude, and then it starts moving away from this high pressure zone. It creates its own gradients, it cools down, it sinks down, and it sinks down, it creates high pressure zone this time, and then the cycle repeats. This time this colder air is moving away, it moves to warmer areas where the pressure is low. So this creates this constant convection cells, and essentially any atmospheric system, any weather system is a result of one or many atmospheric circulation cells. This picture illustrates the development of a closed atmospheric circulation cell because of the surface heating, as we can observe it in the real weather systems. So you can see as the ground is becoming warmer, the air on the ground warms up, it moves upward, it creates high pressure zone at a certain altitude, low pressure zone at the ground, and as this warm air moving up, it then starts cooling down at a certain altitude, it moves away, it again sinks down in areas around. As it sinks down and cools down at the same time, it creates high pressure zones around, and then as it starts reaching the Earth, this colder air in the high pressure zones starts moving back into this warmer area with low pressure zone. So this convection cell mechanism is working at a variety of different scales, from very small convection cells to the huge global systems. And we can certainly illustrate it here with the sea and land breezes that we're experiencing here in West Michigan as lake and land breezes. You all have experienced it. If you have ever been on the beach, you know that in the daytime, the land is warming up much faster than the surface of the lake. And so as the land is warmer and the lake is colder, we see a steady high pressure zone that forms over the surface of Lake Michigan. Likewise, we see the low pressure zone, which is forming over the land. And so at the surface of the lake and the beach, we're experiencing cool air moving from the high pressure zone into the low pressure zone, and that's why it's always cooler on the beach, because we're experiencing this breeze coming from the lake or coming from the ocean. At the same time, the convection cell is just blowing in the opposite direction at a certain altitude. So as this warm air is moving upward over the land, it's then expanding and it's blowing from the land to the lake over a certain altitude, where it then cools down and sinking down. In the nighttime, the mechanism is exactly the opposite, and so the convection cell is blowing in the opposite direction. This time, it's the land that is going to be cooler, and so this is where we would see the high pressure zone over the surface of the land, because the cold air is sinking down, and then as it's sinking down, it starts blowing in the direction of the lake, over the surface of the lake, or over the surface of the ocean, where the temperatures are higher, because water during the nighttime would be warmer compared to the land. And so we'd see this warm breeze blowing from the land into the ocean or into the lake. And at a certain altitude, we would see the opposite direction, the compensatory movement from the lake or from the ocean into the land, as this low pressure is moving air upward and high pressure is moving air downward. A somewhat similar mechanism can be also observed due to the differences in the temperature and pressure between the valley and the tops of the mountains. In the mountainous areas, this is where we would see the valley and mountain breeze. Again, it's a similar mechanism. The warm air would start climbing out of the valley along the slopes of the mountains, and as it's moving up, it would start cooling down, and then as it cools down, it would create a high pressure zone, and then the air would start sinking down into the valley, creating another high pressure zone. So warm air moving up, creating low pressure zone, and then cools down at a certain level within the atmosphere, and then moving down, creating another high pressure zone. At nighttime, exactly the opposite is going to happen, because of this contrast of the temperature and pressure between the bottom of the valley and the tops of the mountains. And so we would see the opposite direction of the breeze, when the cold air would start moving, sinking down, from kind of sliding from the top of the mountains down into the valley. And as it moves down, then the warm air from the valley would be pushed up from the low pressure zone, going up and then creating high pressure, and the cell would kind of close up with the air moving from the high pressure into the low pressure and then sinking down back into the valley. The same mechanism, very similar to breezes, also based on the gradients between the temperature and pressure, can be observed not only at the scale of day and night, as we could see in case of breezes, but also at the scale of different seasons, as we could see in the monsoonal circulation, and operate at much larger spatial scale. In case of monsoon, the gradients are caused by the contrast between the winter and summer weather over the continent and over the ocean. During the winter monsoon, the high pressure establishes over most of Asia, over Siberia and Western China, where the continent is much, much colder compared to the ocean. And so there is this huge contrast between the cold ocean and cold continent and warm ocean, causing very high pressure system to establish over the continent and a low pressure system to establish over the ocean. And the air in winter is moving from the high pressure zone to the low pressure zone, from Siberia, from Western China, from Central Asia, moving this cold, dry, kind of dusty air out of the continent into the Indian and the Pacific Ocean. During the summer monsoon, it's exactly the opposite. At this time, we have low pressure zone over Central Asia and southern Siberia, northern India, over China, the continent is very, very warm relatively compared to the surface of the Indian Ocean and the Pacific Ocean. During the summertime, it's the ocean which is cooler, and so we have relatively higher pressure forming over the ocean and lower pressure forming over the continent. During this time, have very intensive opposite movement when the air is moving from the high pressure over the Pacific and Indian Ocean into East Asia and Southeast Asia and South Asia, bringing lots of moisture. And so this is what we know as monsoon. Most of people refer to monsoon thinking about this movement of very warm and very humid and very wet air that brings lots of precipitation from the Pacific Ocean and Indian Ocean into the Asian continent. But it's correct to refer to monsoon as a seasonal movement of air. So there is both winter monsoon, which is dry and cold, blowing in winter from the continent into the ocean, and then summer monsoon, which is very warm and very humid and is bringing lots of precipitation from the ocean into the continent. So if we could imagine the Earth without the Coriolis effect, without its rotation in space, this is how the simplified model of the atmospheric circulation would look. We have the low pressure over the equator, we have high pressure over the North Pole and the South Pole because the equator is warm and the poles are cold. And so we would see these two hemispherical giant convective cell with the air, with warm air moving upward over the equator and then moving to the poles and then cooling down, sinking down, and then moving in the opposite direction from high pressure to the low pressure over the surface of both hemispheres, from the poles to the equator. So this will be very simple global pattern of the solar radiation that would be just causing this distribution of the temperature. But because our Earth is rotating and we do have the Coriolis effect, three major cells have developed both in the northern hemisphere and in the southern hemisphere in the overall system of atmospheric circulation. So the three sets of cells are the so-called Hadley cells that have developed between the equator and the tropical regions, the Ferrel cells that have developed in mid-latitudes, and then the polar cells that have developed over the North Pole and the South Pole. And each of the sets of cells is associated with its own system of winds, and the system of winds are caused by the movement of the prevailing winds and their deflection by the Coriolis effect to the right in the northern hemisphere and to the left in the southern hemisphere. So in the tropical regions, we see this movement of warm air from the low pressure to the upward over the equator, and then the movement of the cold air over the tropics downward. So as this cold, dry air from the tropics is coming back towards the equator, it is deflected by the Coriolis effect and it creates the system of trade winds, right? We have the northeast trades in the northern hemisphere and the southeast trades in the southern hemisphere. So this is that movement from the high pressure going back to the equator as a part of the Hadley convection cells, deflected by the Coriolis effect. In mid-latitude, we have Ferrel cells. They are not as intense as Hadley cells, but the Ferrel cells, this is where we see the westerlies. So the air here is moving from the high pressure in the 30s in the tropics, and the air is moving from the high pressure into the low pressure associated with mid-latitudes, and this is where we have the jet streams. So this air is also moved by the Coriolis effect, and as it deflected, it's referred to as westerlies both in the northern hemisphere where they're deflected to the right, and in the southern hemisphere where they're deflected from their original destination to the left. And then in the polar regions, we have those two polar vortices that are associated with high pressure over Arctica and over the Antarctic. And so these high pressure zones associated with sinking of very cold air downward over the poles, and movement of this air away from the poles towards mid-latitude is causing creation of the polar vortex. So think of this: three systems of atmospheric circulation and three systems of winds. The polar vortexes are causing easterlies. So the easterlies is the air moving from the North Pole and the South Pole towards mid-latitude, also deviated to the right in the northern hemisphere and to the left in the southern hemisphere by the Coriolis effect. The run of the seasons caused by rotation of the Earth and the tilt of its axis causes the difference of these atmospheric systems and convection cells between winter and summer. So as you can see, in mid-July, the prevailing surface winds and the center of atmospheric pressure are shifted to the north. The intertropical convergence zone, the zone of the low pressure that forms over the equator, is moving northward. And with it, all the systems are also moving northward, and they're shifting into the northern hemisphere. You can see that the equator is essentially moving into the northern tropics, and then the northern tropics are moving further almost into mid-latitudes, and then the lower pressure of mid-latitudes are also moving northward. At the same time, in the southern hemisphere, we also see the same shift, so that the high pressure is moving much closer to the equator, and then the lower pressure of mid-latitudes in the southern hemisphere is also moving north. So everything is shifting north, and this is when we have some of the northern hemisphere, and kind of the equator is closer to the northern pole. And exactly the opposite situation would be in January, when the intertropical convergence zones associated with the equator would actually shift into the southern hemisphere, and then all convection cells and all these three forms of cells, the Hadley cells, the Farrell cells, and the polar cells, would move into the southern hemisphere. So this is when we have winter, of course, in the northern hemisphere and summer in the southern hemisphere. So this is a very quick summary of the key concepts from chapter 5. As always, if you have any questions, please email me or join me on Zoom, and also during the office hours this Friday.